Okay, let me share my screen and we will just remind what we have been doing in the last week. Hope you can see my screen. Okay. We were talking about the silicate minerals, then silicate structures, because under the descriptive mineralogy, you will learn mainly on these descriptive part of these minerals, because you are doing optical part with Dr. Dharma Priya. And for those who were absent last time, probably a couple of you might have not been present in the class last time. So let me recap what we had done last time. Is it clear, my voice?
Very clear for me.
Okay, I hope everyone gets it clear. Right. So we were talking about the predominance of silicate minerals in the Earth's crust. So as you know, the Earth's crust is mainly composed of silicate minerals, and composition-wise, I presented the composition table there. Here you can see mostly oxygen and silicon are the abundant elements in the Earth's crust. So you can see they are occupying a large fraction among the other elements there. And if you consider the minerals, there, and you can see a predominant part, that means this section, okay, is composed of feldspars, right? Either plagioclase or alkali feldspar. So you know the difference between plagioclase and alkali feldspars. So we will discuss about these features as well in the course of some of the lectures in the future. The plagioclase feldspars are mainly like 30, almost 40%, and alkalis around 12%. And you can see the remaining is like quartz 12%, pyroxenes 11%, and amphiboles 5%, micas 5, clays 5, and other silicates. So I think so far you have learned about the other silicates, the minor types of other silicates. They are also occupying about 3%, and the rest is composed of non-silicates. So you know non-silicates, oxides, hydroxides, sulfides, like other minerals which are found in the Earth's crust. It's about like 8%. So as you know, predominance is feldspar, right, according to this data. So therefore, we have to learn much about silicate minerals, because those are the main rock forming minerals that we find in the Earth's crust. So you know, some of these minerals are called rock forming minerals because they are the predominant composers of the available rocks in the crust and the mantle actually. But here we will mainly focus on the silicate minerals. Right. So it seems more than 90% of the minerals in the Earth's crust are silicates. So that is one of the important points. And we learned about the silicon tetrahedra. So what is tetrahedra? Silicon tetrahedra. That is the basic building block of silicate minerals. So silicon tetrahedra is the building block. That means that is the main part of the structure of the silicate minerals. So you can see one silicon tetrahedra. So here silicon element is there, silicon atom is there. So it is connected to four oxygens there, right? So you have four oxygens connected to one silicon atom, right here. So you know silicon is 4+, and oxygen, the valence is -2. So 4 into -2 is -8, and 4 plus. So you are getting a balance of 4 -4. So that means the silicon tetrahedra must be having a valency of -4. So that means it's not neutralized. It's a charged component. It's each oxygen will have -1 because the other electron is shared with silicon. So the total charge is -4 in the silicon tetrahedra. And we discussed about the connection of the silicon tetrahedra to each other. And based on that, the silicates were categorized, right? So how we categorize those, the mode of interconnection between these silicon tetrahedra. Some are how do you say, isolated, okay? Some are isolated and some are connected. So this connection or interconnection can be in different ways, and mainly oxygen serve as the bridge, okay, for connection. So oxygen serve as a bridge for most of these silicon tetrahedra interconnections. So that is what we call the polymerization. Okay, polymerization is just repeating the same structure, same unit in the molecule, and which is accompanied by oxygen, bridging oxygen. We call them bridging oxygens. Okay, so these bridging oxygens serve as the connectors in between these silicon tetrahedra. So we categorize these ones, these silicate minerals, into different groups as isolated ones, mesosilicates, and so connected two tetrahedrons, the sorosilicates, then connected in a ring-like structure, that is cyclosilicates, and connections with like a chain, right? Single chain here, that is inosilicates, and the inosilicates have two types. They are also showing interconnections with two chains like this, and these are also one type of silicate double chains. And then phyllosilicates, here they are having a sheet-like structure, right? You have sheet-like structures, like the pages of a book, you can see, right? For example, mica. And then we have three-dimensionally connected silicon tetrahedra, complex interconnections, which we call tetrosilicates, right? So these are the silicate types, and under these different categories, we have different minerals to get to know, and we discussed the first type, that is mesosilicate, last time, where we have the independent tetrahedra. Okay, so the unit is the unit formula is like this. One tetrahedra is there, which is connected with a cation, and often this cation is +2 valence, right? So in this case, they are tightly packed tetrahedra. Olivine is one of the examples that we learned last time. Okay, olivine is one of the examples, and this X, or the cation, can be substituted either magnesium or iron. So for that feature also we gave a special term, but the details we did not talk at that time. And also you will learn about these things in later stages as well. That is what we call the solid solution, right? I think you can remember the solid solution. Here you have the solid solution. That means interchanging cations in different proportions. So can somebody tell me why we call it solid solution? Yes, can someone tell me why we call it solid solution? What do you mean by solid solution? There are two, see here the formula for olivine. This is the olivine formula. Here you have uh, some specific composition for in the definition of minerals also. We talked about the definition of minerals at the very beginning, where we considered the one feature for a substance to be called a mineral. It should have a definite chemical composition. Okay, definite chemical composition should be there, but now I am telling that the structure, I mean the chemistry can be variable because of iron magnesium exchange. I am now telling. So does it deviate from the definition? Does it deviate from the definition? Yes, I get an answer in the chat box. One is saying composition may sorry, composition vary with a defined limit. Okay, agreeable. So does it deviate from the definition of the mineral? No. Okay. Still the definition holds there because here you don't see any calcium or manganese or anything, right? So it's definite. The magnesium and iron is there in this particular mineral, but of course the proportion is changing, right? That's the only difference. But the chemistry is it's the molecule is composed of iron and magnesium, so that means it must have a definite chemical composition, but the proportions, ionic proportions, can be variable because of this solid solution. So you will learn about these solid solutions and their mechanisms and other features in the future lectures, in other course modules also, in related to the petrology, introductory petrology also, in the next semester. So here we are not much discussing about that, and also you will learn about solid solution separately at the end of this descriptive mineralogy lecture series. After introducing all these mineral groups, we will talk about this solid solution, some introductory aspects. Okay, right. So its solid solution is for those who were absent at that time, it's like a solution, right? Solution means a mixture, right? A mixture dissolved with different materials. So here also you can see materials are mixed, right? These proportions can be variable based on the physical parameters. What are the physical parameters we are talking about in rocks? What are the main physical parameters? Yes, quickly tell someone. What are the physical parameters? So I'm telling that it's variable. Yes. Okay. Oh, hardness. No, hardness is not a physical parameter. Yes, correct. Temperature and pressure. Yeah, I have some answers in the chat box. Temperatures and pressures. Yes, that's correct. And sometimes the availability of fluids is also a matter in case, but mainly the temperature and pressure we consider as the physical parameters, because depending on that only we have these different minerals crystallized at different depths. Okay, pressure, temperature is a matter for that. Okay, based on that variability, on that the solid solution behaviors can change. Mainly temperature is the sensitive parameter for solid solution. Okay, right. So anyway, Mesosilicates, olivine is one of the main examples that we present as for Mesosilicates. There are many other minerals also, which I am not going to present all the examples because you will get an assignment later on regarding finding out about other mineral types, other minerals of different types of silicates. Right, so you will have to have a self study and submit the assignment also. Later on I will give you an assignment. So for the time being, I'm just showing you only olivine as the example. Okay, right. Right, so here the olivine, you can see the magnesium and iron N members can be found. So in solid solution, as I mentioned, the proportion can be changed, right? So one at a certain physical condition, this olivine can be entirely magnesium rich or entirely iron rich. That means 100% magnesium, 100% iron. Okay, ferrous. So such situations, those are ideal situations actually. We term as n-member compositions. Okay, n-member compositions means entirely one of those solid solution minerals elements are rich 100%. Actually, in the nature, if you analyze olivine, you will see both of these elements are there. Very rarely you see these ideal compositions, but we have defined n members for those, right? We call them n members. So magnesium rich olivine we term as phosphorite. Okay, phosphorite, that is Mg2SiO4, and the iron rich one is termed as phthalate. Okay, it's phthalate, iron rich n member. So when they are mixed in different proportions, it's the olivine solid solution component is there, right? So it's all depend on the physical conditions, mainly temperature dependent behavior is there, right? That's about one of the Mesosilicates, and I forgot to tell that sometimes people term these Mesosilicates as island silicates as well, because they are independent tetrahedra. Okay, right. So some features of olivine, you can see their physical properties. I think in the first year you have already learned about these basic features. Just to remind you, it's a high temperature mineral, mainly in igneous rocks you can find, especially in the, tell me where you can see a lot of olivines in the earth, a place where we can find a lot of olivines in the earth. Yeah, quickly tell someone. Where do we
Earth
get?
mantle.
Very good. Yes, Earth's mantle. In the Earth's mantle, we have a lot of olivines because there are a lot of peridotites there. Okay, peridotite is a specific rock type which contains iron, magnesium, rich minerals. That means ultramafic rock type. Okay, so we will learn about these rocks in the introductory petrology course in the next semester. Okay, so olivine, it's a greenish mineral when it's magnesium rich. So when it iron rich, it becomes more blackish. Okay, in some periodites, you will see very black olivine. So it's called black periodite. Some people call, right, because it's olivine rich. Then it's a special rock name called dunite. So some people call it black dunite when it's iron rich, entirely rich. So anyway, some some gem varieties are also there, peridot, right? It's also deriving from that name. When it is magnesium rich, it's very beautiful. It's olive green. It's a real olive green mineral. And most of the cases, it's having equigranular to prismatic habit and no cleavage, poor cleavage is there, olivine. Like quartz, we don't have a proper cleavage in olivine. And under the microscope, I don't think still you get a chance to see the optical images of olivine. It's colorless to it can have a high interference colors. under the thin section. So we will see when you are able to come to the university, when we do practicals, some optical properties of these minerals, because we don't see these olivines in our rocks commonly, because our rocks are mainly crustal rocks, they are not mantle rocks. But in some marble you can see some olivines. Okay, marble rock, marble, metamorphosed limestone, right? So don't worry, we will learn about these things under introductory petrology. Okay, so there is complete solid solution between iron and magnesium, as I mentioned before. Here are some phase diagrams. So at the moment it's a little bit tough for you. We will learn about phase diagrams later on. Okay, right. So the other mesosilicate, that is garnet. Okay, there is another very common mesosilicate type, that is garnet. So you already know about garnet. Tell me about very characteristic optical feature of garnet, because you have already learned about optical mineralogy now, the principles. So can one of you tell me very common feature of garnet? It makes very easy for us to identify garnet under thin section. Yes. Sorry, I didn't get you clear. Isotropic. So isotropic mean what is observation under the microscope? Yes, cubic, it's correct. What is observation under microscope then? How do you recognize them?
Oh, interference color.
Interference color, yes. What is the interference color?
With cross-polarized.
Okay, yes. We get the interference color when you cross the polars. Yes. What is the color for giving by garnet?
Continuously observe black color.
Okay, it's continuous black. When even you rotate the stage, nothing happens, right? So it means isotropic. Okay, so that means you don't get any light out of the second polarizer. That's totally absorbed, right, in both directions. So that is isotropic feature. So that's very good. So it's any other mineral you know about such similar feature? Isotropic feature. Have you learned any other mineral which shows isotropic characteristics? No, not yet. Okay, spinel. Spinel is one another type. Okay, and fluorite is also one more. Yeah. Okay. Good. Right. So garnet is having a bit complex chemistry because there is ample opportunity for replacements, solid solutions. Here also you have the solid solution behavior, very well observed solid solution behavior. So that makes garnet to have crystallized in different varieties. There are several types of garnet available because of this complex chemistry which is available in the garnet structure. So this is a moderate to high temperature mineral, but mainly garnet needs some rich aluminium compositions in the protolith, in the rock. Okay, in the parent material you must have a lot of aluminium. So therefore we consider aluminium rich sources. That means sediments or aluminium rich components. Okay, and also there are different types of garnets. Anyway, we will learn about the details later on. And usually equigranular euhedral to subhedral habit is there. Also some poor cleavages are present. A lot of fractures you can see in garnet, right? I think you have already observed some features, not physically, but at least by images during the online teaching. You may have seen some images, okay? And they have very nice crystal structures. Dodecahedra crystal structure is there, right? So you just recall your first year knowledge crystallography, about the shapes of this garnet. So anyway, this common formula you can consider as A3B2Si3O12. So this, when it comes this common silicate composition, you can recognize that it is garnet. Okay, so this A and B can be replaced by many cations. As I said, that this has a complex chemistry. So usually A site. So we call some crystallographic sites as A sites and B sites. Okay, so here you have a diagram of garnet, which you can see tetrahedra of silicon tetrahedra are attached with cations. Okay, so we have A sites and B sites. That means some crystallographic places where the cations can be accompanied, depending on that. So we will learn about the complex structures later on. This is the introductory stage. I don't want to make you bothered on this crystal chemistry, but just keep in mind that there are two main crystal sites there. Here A site and B site we call. There you can see some cations, iron, magnesium, calcium, and manganese mainly can replace there. And the other side, where you have the the aluminium is connected. Okay, aluminium is connected. So these two sites can replace different cations, so that variable compositions of garnet can be observed in the field. Okay, so one of those compositions is the iron-rich component. So as I mentioned in the previous case with olivine, there can be some ideal situations. Ideal situations means one of these cations are enriched there, maybe 100% in ideal situations, or otherwise more than 90% of that, plus other cations in minor amounts. So such a composition we term as N-member composition, right? So for garnet also the same thing holds. When it rich in iron, we call it almandine. So the garnet is almandine garnet, we call, right? It's a special name for that particular garnet. It's almandine variety. And similarly, you have pyrope garnet. Okay, that is magnesium-rich garnet. Almandine is iron-rich garnet, and spacetine, you have the manganese-rich garnet, and grossula is the calcium-rich garnet. Okay, there is another one called andradite, where you have calcium and iron both, right? And aurovite, where you have the chromium component, right? Especially the chromium is there with calcium. So these are the varieties of garnet you can find as N-member compositions, and because of this complex solid solution behavior, right? So this makes garnet to have a variable composition. So you know the solid solution behavior is controlled by mainly temperature, as I mentioned, because of physical parameters, and also pressure dependent in some cases. And in high pressure rocks, you have like eclogites, right? You have also again this type of different garnets found. Okay, so this garnet can be variable, whether irrespective of whether high temperature rock or high pressure rock, because the solid solution behavior is a matter of variable pressure and temperature conditions. So it's mainly controlled by that. Okay, so anyway, another mesosilicate, a very common mesosilicate is garnet. So this has a complex chemistry with respect to olivine. So here olivine, you see a very simple chemistry is there, right? In the ideal situation, you have only one of these. So it's a very simple chemistry. But the garnet, you can see it has a complex chemistry. So actually, if you analyze, we can analyze these minerals independently using nowadays we have dry methods. Not like in old days, there you have to do some titrations and find the compositions using wet chemistry methods. But now we have dry chemistry methods. That means directly you can even use the your thin section, rock thin section. I think Dr. Dharmapi might have taught you about the rock thin sections. Preparation of rock thin section. You also have to make each of you have to make rock thin sections. Those are the samples that we use to study under the microscope, polarizing microscopes. Okay. So even this rock thin section, that is 0.03 millimeter thick section, can be analyzed by a special equipment called EPMA, electron probe microanalyzer. That is an electron beam is bombarded to the thin section, and depending on the emitted secondary X-rays, we detect the compositions, right? Under in your third year, you have a separate course module called analytical techniques. There you will learn about the details of these technical procedures, etc. So anyway, we can analyze these minerals using an electron microscope or EPMA. There you can recognize the composition, okay, the mineral composition on the sample itself without destructing the sample. Electron beam does not make any destruction to the sample, right? So, but the natural samples, when you analyze like that, you will see very rarely you will see these end-member compositions, these ideal compositions. Sometimes we call ideal compositions, but you will see a mixture of these cations in variable proportions in the garnet structure, natural garnet structure. Okay, right. So this is the various types of garnet. You have to remember these compositions. Which one is magnesium rich? Which one is termed or in other words, if someone asks what is spazatine, then you should know what sort of a garnet it is, right? And also you see their colors are physical properties. I think some of you got confused when I asked about the physical parameters. One answered me hardness. It's a physical property, okay? It's not a physical parameter where the rocks are undergoing. It's a physical property, right? So color and all, those are physical properties. Anyway, the colors are different in these different compositions. So you have deep red, deep brownish, and actually the almandine also, it's coming in deep red also. Okay, so you remember, yeah, brownish red it says, but yeah, it's anyway, you will see the samples physically later on. And spazatine, brownish, grossular yellow green varieties are also there, but the brownish varieties are more common in grossular. Androtite having variable shades of colors, and white is mostly greenish, emerald green. Okay, right. So all depend on their chemistry under which these minerals were crystallized. So different crystallization mechanisms are there depending on the environment. Environment means the source compositions, the physical parameters, the depth within the crust or the mantle, like that. Okay, so all these details you will learn under other course units in the future. Okay, do you have any questions up to now? Any question regarding this content? Please put your registration number in the chat box to record the attendance. Because as I said the last time, the Learn platform deletes some records after 1 month's time. Therefore, if you put in the chat box, that will be kept permanently. So it will be easier for us to track your records. Any question? Or anything which was not clear? Okay, it seems we can proceed further. So back to the silicon tetrahedra or the polymerization, we covered Mesosilicates so far, and next is Sorosilicates. So in the Sorosilicates, we have the double tetrahedra. Okay, double tetrahedra, which are having connected with the bridging oxygen. Okay, bridging oxygens, they share electrons. They share two electrons. So with two silicon, sorry, they share electrons. Right, sorosilicates. So double tetrahedra, usually you're having this type of component there, and one bridging oxygen is there. Right, here is a bridging oxygen. You can see clearly two tetrahedra are interconnected. Okay. Typically, they are having monoclinic symmetry. So you can remember your crystallography knowledge in the first years. So you can see they are having a monoclinic symmetry, right? So one axis is inclined. Here you can see that clearly. So epidote is one of the examples. So this is one of the minerals we find in some rocks. It is a greenish mineral. This is one of the examples for sorosilicates. Okay, and sorry, a zoisite, clinozoisite, right? Epidote. So these are epidote group of minerals where you can see further complex chemistry is available there, right? You see calcium, iron, aluminium, they are complexly bonded, connected or bonded with this silicon tetrahedra, this unit, and some hydroxyl ions are also attached. So this mineral is different from what we learned before, because this hydroxyl group can also be attached there, right? Possibilities there. But for garnet or olivine, there is no way for this hydroxyl group to be attached. So they are called anhydrous minerals or dry minerals, the garnet, olivine like minerals, but these are having OH group. That means it's hydrous minerals. We call them hydrous minerals. Okay, so there are different aspects, features related with these hydrous and anhydrous minerals, which you will learn under petrology, introductory petrology, in the next semester. So this is a common mineral found in many rocks, in igneous rocks, and also in metamorphic rocks of various types. So igneous and metamorphic rocks, I think you have learned some very introductory or very preliminary knowledge at your first year regarding these rock types, different rock types, right? And the different minerals can be found depending on their rock type also, right? So zoisite is orthorhombic, and clinozoisite is, for example, you are having epidote like minerals, they are monoclinic symmetry, right? So physical properties, just remind I think you have to recall your first year knowledge as well. So hardness and the colors, right? You may be remembering, some of you. So please go to your first year notes as well, right? Otherwise, you will have to learn from the very beginning. Okay, So optical properties are also their variable optical properties. So which I think these physical and optical properties I don't have to detail much because you have learned already them. What you have to do is you have to revise your knowledge. Okay. Uh, some I don't think still you have learned about these some of these features, optical features. Dr. Dharmapriya sir will teach you about these things later on because it needs some practical knowledge also to understand these optical properties, these biaxial features. Anyway, but you know very clearly about these basic features like relief, these optical features. But of course, with images, you may have seen the relief, right? Have you learned about the basic optical properties by now? Relief, pleochroism like features, basic features. I hope you have covered them so by now. Okay. Yeah. Anyway, you will have opportunity to see these features physically once you come to the university when the practicals are started. Okay. So these zooids, epidotes, they come under this particular group of sorosilicates. Okay, right. So just remember the difference between mesosilicates and sorosilicates. Mesosilicates are single tetrahedra and sorosilicates are double tetrahedra. They are interconnected with a single bridging oxygen. Okay, right. Right. So do you have any questions up to now? So as I said before, you will have to find other minerals which belong to these different groups. Okay, and give a. I will give you the proper assignment. So based on that, you have to submit the answers by referring other sources as well. Okay, right. So going back to the silicon tetrahedra. Mesosilicates, sorosilicates, and the next type is cyclosilicates. So it's a like ring type structure. Okay, ring type structure. It's a ring silicate type. I mean, some people call it ring silicates because they are interconnected in a manner of a ring like. So that's why it's called cyclosilicate. So we will learn about that thing also. Just a minute. I will stop share at the moment. Okay. So now we will move to the cyclosilicate part as well, because as you can see here, this is the type. Okay, ring type structure. This one, right? So they are rings actually, cyclosilicates. So there you have this type of uh, silicon structure, the unit composition, and these silicate minerals show some hexagonal and orthorhombic symmetries. Okay, hexagonal and orthorhombic symmetries, and usually poor cleavage also, right? Usually poor cleavage as well. right? So some of the examples. Okay, before that, you can see the rings. These are the rings. Okay, in the crystal structure, they are joined. Okay, so this is a ring type structure. So it's also a sort of a complex structure. So you can see here how they are interconnected. Sorry. So depending on these rings, there can be different types of cyclosilicates formed. So we will learn about the details later on, but just we'll go through some introductory aspects of some such minerals belonging to this family. So beryl is one of the examples. So have you heard of beryl? Beryl is one of the minerals. It's also in the form of gem varieties also, like these gems, right? It's a common accessory mineral in igneous rocks, particularly in pegmatite. So there is a rock type called pegmatite. I think you will have learned about this thing, this pegmatite. The term maybe you are familiar with, but details you don't know, of course. We will learn about these rock types, as I said, in the next course units. Okay, and beryl is one of the examples belonging to this cyclosilicate family. And cordierite is another mineral, which is a common mineral in metamorphic rocks, not only contact metamorphic minerals, actually. In regional, in other metamorphic rocks also you can find. So we will learn about that things later. Don't bother much about these, some of the terms which I'm using here. Anyway, it's again, these are also some solid solutions. There you have a lot of replacements with respect to the temperature variations and all. And also it's again aluminium rich mineral. It needs aluminium in the protolith. Protolith means the parent materials. Okay, we call argillaceous rocks. Argillaceous rocks means the rocks which were formed by aluminium rich materials. Okay, sometimes this looks like quartz, but in the hand specimen, but really it's different from quartz. Okay, and tourmaline is another example for this cyclosilicate. But you see the formula. So this is actually the natural formula. I mean, when you analyze tourmaline, you will see this type of very complex formulas. It's not the ideal composition anyway, right? So a lot of cations can be replaced there because it's a cyclic structure. It permits having a lot of interconnections with cations. Okay, so this mineral is also a gem variety, and also it is considered as an accessory mineral. So what is an accessory mineral in a rock? Can anybody tell me just about what is an accessory mineral? Maybe you didn't learn it in detail, but some of you may have heard at least. What's an accessory mineral? Can anyone answer? No? Okay, accessory minerals means the minerals which are found in less abundances in rocks. Usually we have very limited quantities. Okay, but cordierite is not an accessory mineral, but it can be an accessory in some rocks probably. But usually we term accessory minerals as those which are having in less abundances, like 2%, 1%, like abundances. Okay. Anyway, the tourmaline is one of such minerals. So under cyclosilicates, you can have beryl, cordierite, tourmaline as some examples. Okay, so these are ring silicates. So remember, they are having a ring type structure as their building structure. So so far we could cover Mesosilicates, right? Some basic aspects of Mesosilicates, Sorosilicates, and Cyclosilicates, right? So there are three groups of silicates we briefly considered about their features in terms of the silicon tetrahedra based on the arrangement of that particular tetrahedra. Okay, so it's I mean these these categories are not having very complex chemistry in terms of the polymerization, but of course the cationic replacements, there is opportunity for replacing, because equal size cations can be replaced to each other, right? So and also the valency matters. You can have to learn opportunity later on about these mechanisms of these cationic replacements in different minerals. Okay, so today actually I have to finish with this short lecture because today the officers and other all activities will be becoming to normal conditions, at least to some extent. So therefore I have to be in the department, and there is a meeting also. So therefore in 1 hour's time, I mean it's almost time to stop the today's lecture, but the next week again I will take 2-hour lecture as usual. Okay, so do you have any questions up to the content that we have covered so far? If you have a question, you can just post now. No questions? Okay, in the chat box also, let me check. No question. Okay, anyway, so we'll stop here for today, and we will meet the next time. Okay, and at the same time, I think yesterday you had a some demonstration session by the our demonstrators, right? Did you have it? You have to attend. Yeah. Okay. You have to attend. Okay. You have to attend to those sessions also. Those are very important, because you are not having any practical exposure so far. So therefore we are trying our best to show you some videos at least. They have prepared some videos using the laboratory facilities in the geology department. So you might see some of these optical features as well, with the aid of some videos at least for the time being. Okay, so and also this type of lecture, I mean course module like optical mineralogy, it's very hard to learn without your own observations with your naked eye through the microscope. Okay, so some aspects maybe you have already realized that it's very hard to understand, right? So therefore as a support for that, we are trying to show you some of the videos uh, created to help you to understand these some of these concepts. So therefore please attend those sessions as well without missing them. Okay, right, it's very important. Right, okay, let me finish for today, then we'll meet next time. Okay, have a good day. Thank you, sir.
Thank you.